So far we have discussed the material properties and how this would change in 2D, and we saw that this is going to be different for C. Now, the second part is related to the relation between the displacement and the strain, so the U and epsilon. Now, obviously, in 1D, you have only one direction, and you have displacement happening in this direction. So the derivative of U with respect to X would be the strain. Now, if you look into 2 dimensions, you have X and you have Y, and you have objects that are 2-dimensional. Then in this case, you have displacement in the X. I'm going to call this displacement U, and displacement in the Y, I'm going to call it displacement V. So every single point here, every single point here can move in the X and the Y. So this is displacement in X, and this is displacement in Y. All right, now because of that, the strain also would be dependent on the displacement in the X and the displacement in the Y. Now, this figure here is related to the infinitesimal strain tensor. So it's related to a specific definition for the strain. But in simplifying, I don't want to get into the discussion of the strain. This is continuum mechanics. But I just want to move directly to the relation between the displacement and the strain. So if you look into the displacement in the X and the strain in the X, this is still the derivative of U with respect to X. If you look into the displacement in the Y, this is now, and the strain in the Y, so this is now the derivative of V with respect to Y. This is the normal components of the strain. Then you have a shear component for the strain. This is gamma Y, gamma XY is meant to be. Sorry, gamma XY. And this is the derivative of V, basically the displacement in the Y with respect to X, and the derivative of U, which is the displacement in the X with respect to Y. So this would define a rotation. All right, so this is now the relation between the stress between the strain and the displacement. It has fundamentally changed, right? So you have 1, 2, and 3. In the past, you had only 1. So how this is going to reflect into the relation between the strain and the displacement here. Okay, so I'm going to develop our first 2-dimensional element. I'm going to follow exactly the same steps we have in here, and you see that they are quite similar, but very similar. Once we get into the strain, I'm going to show you that once we get into the strain, I'm going to show you how to treat the strain. Okay, so I'm going to develop our first 2-dimensional element. And as I said, you will see that everything would follow exactly the same thing. In the past, you had only xi. In 2 dimensions, I'm immediately jumping into the global coordinates, into local coordinates, because there's not much point in discussing local coordinates. Okay, so we're going to build on what we have done in the 1 dimension. So in 1 dimension, you had only xi. In 2 dimension, you have xi and eta. We are going to develop our first element. I'm going to rewrite the whole thing. So everything, pretty much everything we have here, I'm just looking for the 1-dimensional elements. I'm going to reinvent it for the 2-dimensional element. We are going to develop our first 2-dimensional element. As I said, we have xi in 1 dimension. Now we have 2 directions. So we're going to have xi and eta. So this is a 2-dimensional space now. The first element we are going to develop is going to be the simplest possible element. So it's going to be a triangle. The triangle will have 3 nodes, node 1, node 2, and node 3. So this is node number 1, this is node number 2, and this is node number 3. The triangle would run between 0 and 1. So the first node is located at 0, 0. The second node is located at 1, 0. And the third node is located at 0, 1. Okay, so I'm going to take this element to a new page and start by deriving the shape functions for this element. We put it here. Just move it slightly. Oops. Okay, so if you think about the displacement function, I mean, you remember we did always the shape functions relative to the displacement. It is going to still be correct here. The displacement now are going to be a function of x and y. So the displacement now will not be a line in the past. We have the shape function n1, and this is x, to be 1 here and 0 here, right? So at the first node, it is 1. At the second node is 0. So this is the first shape function. The second shape function did the opposite. So it was, this is n2. So it was 1 at the second node and 0 at the first node. Now, the same behavior would also happen in 2 dimensions. So the first shape function, which is associated with the first node here, is going to be 1 at the first node and then 0 here and 0 here. So I'll probably try to draw it. It's not going to be very easy to draw this. I'm struggling to draw things in 2D, so it will be even more messy to draw it in 3D. So this is xi, and this is eta, and think about this as the shape function number 1. Okay, so this is our triangular element. This is the first node, this is the second node, and this is the third node. I'll just put the numbers here, 2 and 3, so that you can see them in relation to these nodes. So the first shape function is going to be 1 at this node, the first node, and then it's going to drop to 0 at the second and the third node. So this is the triangle that is going to happen. Now, if you think about this, this is a function of a plane. So what can describe this triangle is going to be a plane. So now you need, for the displacement, to use, I mean, in the past, we used an equation for a line because we know that this is a line. So it was ax plus b. Now we have a plane. So this is going to be an equation for a plane. A plane can be defined, a unique plane can be defined using one node and a line. So define a plane by a line and one node. This is a unique plane, or define it by 3 points. This is again a unique plane. So this is enough information to define a unique plane. So the equation for the plane is going to be a xi plus b eta plus c. All right, so this is the equation now we are going to use for the interpolation. I'll just remove this because we don't need that. All right, and I'll shift this here for the time being. Now, at the first node, you have xi is equal to eta is equal to 0. And at this point, you have u to be equal to u1 is a multiplied by 0 plus b multiplied by 0 plus c. And from this equation, you would immediately get c is equal to u1. Now, at the second node, I'm just following the exact same procedure we did for the one-dimensional element. It's exactly the same. Nothing has changed. At the second node, we have xi is equal to 1 and eta is equal to 0. And then we have u to be equal to u2. So this would be a multiplied by 1 plus b multiplied by 0 plus c. Now, you know c already is equal to u1. So I'm just going to replace it with u1. And then this will vanish, and I will have a to be u2 minus u1. And I've got my second unknown. And then at the third node, we have xi to be 0 and eta is equal to 1. And then in this case, u is equal to, this will give us u equal to u3 is equal to a multiplied with 0 plus b multiplied with 1. And I'm just going, instead of c, going to write u1 because we know that this is equal to u1. This will vanish, and b will be then, in this case, u3 minus u1. Right, I have a, this is a, I have b, this is b, and I have c, this is c. I'm just going to take them and substitute all of them into this equation here. So this will go here, this will go here, and also b will go here. Okay, so my equation then is going to be U is equal to A, this is U2 minus U1 multiplied with xi, added to B, this is B, it is U3 minus U1 multiplied by eta plus C, this is U1. Now, just like I did in the past, I'm going to have everything to do with U1 first. So this term includes U1, this term includes U1, and this term includes U1. I'm just going to put them first. So I have minus U1 xi minus U1 eta plus U1. And then everything to do with U2, I put it second, is only one term. It is U2 xi. And then the last one is U3 eta. Take U1, U2, and U3 as common factor is going to leave me with U1 multiplied by 1 minus xi minus eta plus U2 multiplied by xi plus U3 multiplied by eta. And this is going to be my first shape function, and this is my second shape function, and this is my third shape function. So my shape functions are now n1 is equal to 1 minus xi minus eta, n2 is xi, n3 is eta. So these are the shape functions. Oops. Just throw it again. Okay, so these are the three shape functions I have. And now I can write you so n1 and n2 and n3 are the shape functions. Okay, so we have them here. I'm just going to show you what we did for the, oops, sorry. So we have the shape functions for the one-noded element. We have the shape functions for the one-dimensional element. We have the shape functions for the two-dimensional elements here. So n1 is 1 minus xi minus eta. n2 is xi. n3 is eta. Okay, so we have the shape functions. In both cases, this is the new set of shape functions. Now, we have the displacement to be written in terms of the shape functions. So I'm just going to rewrite the displacements in terms of the shape functions here as well. So U is equal to N1, N2, and N3 multiplied by U1, U2, and U3. But also in this case, we have V. I mean, it's not just displacement happening in the X direction, also displacement that is happening in the Y direction. So we have also V, that this is going to be N1, N2, and N3 multiplied by V1, V2, and V3. Now, usually it is possible to write U and V in the same matrix because we have a single matrix for displacement in the one dimension. We also want to have a single displacement matrix for the two dimensions. So I'm just going to rewrite these two equations here just as a single equation, just a matrix notation, using matrix notation. So it is U and V as a vector would be equal to, I'm just going to rearrange this so that I can pick the components that I need, and the components I don't need are going to end up being 0. So I have N1, 0, N2, 0, and N3, 0. And then on the second row, I have 0, N1, 0, N2, and 0, N3. This is multiplied by, it's multiplied by a vector. This is U1, V1, U2, U2, V2, and U3, V3. For the time being, I need the stiffness. I'm just going to remove that. Now, if you multiply this with the first row, you'll see that U1 will be multiplied by N1, v1 will be multiplied by 0 because u is interpolated only using u1, u2, and u3. It's not interpolated using the v. Okay, so this will cancel the v, and n2 multiplied by u2, 0 multiplied with v2, and so on. If you look into the v component, you'll see that it is 0 multiplied with u1 and n1 multiplied with v1. So this way you cancel the component that you don't need and you keep the ones that you need. All right, so we have an expression for the displacement, just the same like the expression we had for the one-dimensional case. Now we need to have an expression for the coordinates. We have coordinates x and y. Before we had coordinates only x. Now we have x and y are interpolated exactly. I mean, if you look into the coordinates here, you see that u and x are treated exactly in the same way. This is also going to happen in the same way once we move into 2 dimensions. So x and y can be written in this way. This is n1, 0. I just copied the whole thing. I think it's better than right. And then we have here x1, y1, x2, y2, and x3, y3. So in this case, if we have any triangle that you are going to map, for example, we have a general triangle that looks like this. This is node 1, 2, and 3. And this is located, I don't know, at 5.3. And then you have 7. For example, here you have that at, I don't know, probably 2.5, and then 3.5, for example. And then this other coordinate is located at, I don't know, 1. And then you have probably 2. All right, see, these coordinates then will be mapped into these coordinates here using this relation here. So this is the relation you are going to use. Okay, so now you have the displacement, you have the coordinates done exactly and treated exactly in the same way like you did for the one-dimensional case. Now we come to the strain. Now the strain is a little bit tricky, so we need to do it properly. I just probably need to pay attention to the strain. So we said the strain is basically the B matrix multiplied by the displacement. Okay, and the B matrix is the derivative of n1 with respect to x, n2 with respect to x, and n. I mean, we had only 2 nodes in this case, so this is the B matrix. Now we cannot have that. Instead, we have the Jacobian multiplied by the derivative of f1 of n1 with respect to psi and n2 with respect to psi. So to find the strain, the first thing we need to do is to find the Jacobian. So I'm just going to do the Jacobian first, and then I will come to the strain. We know from before the Jacobian is the derivative of x with respect to psi. This is what we have. Now, or this is what we had in 1 dimension. Now, in 2 dimensions, we have x and we have y and we have psi and we have eta. So the expression for the Jacobian in 2 dimensions is going to look like this. In 2D, this is going to look like this. Now, this is again math. I'm not going to explain why the Jacobian would mean this because this is rather a lengthy explanation. I don't want to get into that, but I'm going to write the expression, and if you are interested in the math, then let me know. I will show you where to find the math detail. So the Jacobian in this case is going to be the derivative of x with respect to psi, the derivative of y with respect to eta, the derivative of x, with respect to psi, and the derivative of x with respect to eta, the derivative of y with respect to eta. Now we are writing down a matrix. So now the Jacobian is truly a matrix. You can see, I mean, before it was just a scalar. Now we have a proper matrix. Now, the derivative of x with respect to psi, in the past, we found that as the derivative of n1 with respect to psi, the derivative of n2 with respect to psi multiplied by x1 and x2. This is how we found the Jacobian before. Now we are going to do the same thing here. I'm just going to do the same thing for this big guy here. So it's going to look quite lengthy. I want you to bear with me. So you are going to have the derivative of f of n1 with respect to psi, n2 with respect to psi, and n3 with respect to psi. The derivative of n1 with respect to eta, n2 with respect to eta, and n3 with respect to eta. This is multiplied now by x1, x2, and x3, u1, u2, and u3. All right, so x1 is multiplied by n1, and then is multiplied by eta. The same is true for x2 is multiplied by this and multiplied by this, and so for x3, u1, u2, and u3, and then you will end up having these 4 entries. Once you have the Jacobian, you multiply the Jacobian with the derivative. I mean, I'm talking now about the two-dimensional Jacobian. Once you have the Jacobian, you inverse that and you multiply it. This is going to look like that. I'll probably just write it in the full size. I think this is easier to see. X with xi, y with xi, and x with eta, and y with eta. This will be multiplied by the derivative of n1 with respect to psi, and the derivative of n1 with respect to eta, and it will give you the derivative of n1 with respect to x, and the derivative of n1 with respect to y. Now, if you do that, obviously this is inverse. If you do that, you have n1 with respect to x and n1 with respect to y. You need to repeat the same thing for n2 and n3. So this is 2 and 3. This is 2 and 3. The Jacobian matrix would remain the same. It would not change. But you need to do this for every single shape function, and then you get the derivative in the global coordinates. Once you have the derivatives in the global coordinates, you can get the B matrix, which is slightly more nasty than this. Now, this is what you had in the B matrix in the past, n1 with respect to x, n2 with respect to x, because you only had this to be u with respect to x. Now you have it with respect to x and y, so I'm just going to rewrite that, which is the full size of the nasty thing. So epsilon is going to be derivative of u with respect to x, derivative of v with respect to y, derivative of x with respect to y plus, sorry, not x. The derivative of u with respect to y added to the derivative of v with respect to x. This is how the u would look like as a vector at the 3×1 vector or 1×3 vector. And then the derivatives now would look like this. And I want you to bear with me. n1 with respect to x, 0, n1, or sorry, n2 with respect to x, 0, and n3 with respect to x. And you have a 0 there. I'm just going to move this slightly because I need the space. Probably even further. So this is the first row, and then I have n1. Sorry, this is meant to be 0. n1 with respect to y, 0, n1 with respect, sorry, n2 with respect to y, 0, and n3 with respect to y. And in the last row, I'd have dn1 with respect to y, and dn1 with respect to x, and then dn2 with respect to y, dn2 with respect to x, dn1 with respect, sorry, dn3 with respect to y, and dn3 with respect to x. Now, this is the B matrix. This is here is the B matrix, the full B matrix. And if you look into the strain, you will see that the strain is basically the B matrix multiplied by U. So in this case, you have U and you have V. So it is the B matrix multiplied by U1, U2, and U3. And then you have, sorry. You need to have U1, V1, U2, V2, and U3, V3. All right, so if you multiply U1 with N1 and U2 with N2 and U3 with N3, you will get U with respect to X. If you multiply V1 with N1 and V2 with N2 with respect to Y, and V3 with N with respect to Y, you will get the derivative of V with respect to Y. And for the shear, you need to have U1 with respect to Y and V1 with respect to X. You're switching the components, and you repeat that, you will have the shear components. So you have, this is a 6 by 1 vector multiplied by a 6 by 3 or 3 by 6 vector, and the multiplication is going to be 3 by, the multiplication is just going to be this. Three shear component, or 3 strain components, epsilon x, epsilon y, and epsilon x, y. Now, this is the B matrix. The B matrix is always the matrix that connects the strain to the displacement. So this is the B matrix here. And it is a lot larger, and it gets even a lot more complex once we move into 3 dimensions, or once we consider higher order elements. So I've considered the simplest possible element. This is the 3-noded element, a triangular element, but we could have considered much more complex or high order elements. Then the matrix would have looked a lot more nastier. Now we have the B matrix. We're going to use this B matrix to get the stiffness matrix, because we have the B matrix to be like this. And this is the last step I'm going to do. It is how to calculate the stiffness matrix. So the stiffness matrix now, we are talking about 2 dimensions. So I'm just going to rewrite it for the 2-dimensional case. So the K matrix now is, we had the cross-section or the area in the past. Now we have the thickness. I'm just going to call the thickness T. And we have the integral over xi and the integral over eta. So this is running between 0 and 1, 0 and 1. We have the B matrix, which is the B matrix we have so just below, transposed, multiplied by D, multiplied by the B matrix again, and multiplied by the determinants of the Jacobian, integrated over xi and over eta. All right. Now, this here is a 3 by 6 transposed, so it is going to be 6 by 3. So 6 by 3. This is a 3 by 3, and this is 3 by 6. and the Jacobian is just the determinant of the Jacobian, just a scalar, and then you integrate. So the result is going to look like a 6x6 matrix, because you start with 6 rows, you end with 6 columns. So the resulting stiffness matrix is going to be 6x6, and every single component of that will need to be integrated between 0, 1, 0, 1 for xi and for eta. Okay, so this is how the stiffness matrix would look like. Now, I think it is probably a lot to digest, but at the same time, this is probably the simplest way to present it. Now, you need to go over this on your own and see how you understand it, and then you probably can come and ask me also questions if you want to ask anything in relation to how we develop the stiffness matrix for the 3-noded elements. So once you have the stiffness matrix for the 3-noded elements, the assembly process would work the same. So you build the global system of equations in the same way like before, and you solve this global system of equations the same way like before, and you get the solution. All right, if you look into the notes, you'll see that I've derived the equations for a 4-noded element, which is slightly more complex, but I always prefer in the lecture I do the 3-noded elements, and in the lecture notes I put the 4-noded elements, so that you have 2 elements developed in the 2-dimensional case. And you'll see that this is done exactly the same way like I did it in the 1-dimensional case, and also I did it for the triangular element. You'll see that first we have the shape functions n1, n2, n3, and n4. And then we have the displacement written in terms of the shape functions and the displacement vector. The same is also done for the coordinates. And then you have the Jacobian. The Jacobian in 1D would look like this. This is how the Jacobian would look like in 2D. And you need to identify the components of the Jacobian. So this is how you identify the components of the Jacobian. You have the strain. These are the components of the strain, and you just multiply them. You get the strain vector, which is here. And then this is the B matrix as well. So this is the B matrix. The B matrix, you get the components of the B matrix. So this one and this one, using the inverse of the Jacobian, you repeat the same thing for this one, and so on for all of them. So you get the components of the B matrix. Once you have the components of the B matrix, you multiply it with the D, which is the relation we found for the plane strain or the plane stress case, multiplied by G, multiplied by the determinant of the Jacobian, integrated between -1 to +1. And this way you have the stiffness matrix. Now in this case, you have not 6 components, you have 1, 2, 3, 4, 5, 6, 7, 8. So here you have 8 by 3 multiplied by 3 by 3 multiplied by 3 by 8. So the resulting matrix is going to be 8 by 8. So the stiffness matrix for this 4-noded element is going to be 8 by 8. And you have elements that are much larger than this, and especially once you get into 3 dimensions. Okay, so as I said, you need to go through this in your own time. You watch the recording if you want, and then I'm hopeful you would be able to see things in a better way. Always try to think in terms of the 1-dimensional problem, and this is why it's really important to understand the basics, the 1-dimensional, before you move into the 2-dimensional thing. And this is why I say that the finite element method will need to build on previous concepts. So you always need to understand the first bit before you move to the next bit, because otherwise you cannot immediately understand the 2-dimensional problem. This is not possible. All right, so I finished explaining the 2-dimensional elements. Now I can answer any questions related to these 2-dimensional elements. So if you have questions related to what I have discussed in the past half an hour, okay, so I will discuss now some aspects of these elements which are very similar. I mean, some of them will be similar to what we have discussed earlier, but now you can see the full impact of these elements. And first of all, the order of these elements. So we have discussed the 3-noded element. This is linear element. and we discussed four-noded elements. This is, I mean, we call it linear, but it is bilinear element because if you look into the shape functions are multiplications of two coordinates. So it is not an equation for a plane. A truly linear element is this three-noded element because the shape function is really a plane. Whereas if you look into the four-noded element, the shape function doesn't look like a plane. It looks slightly curved. So this is the shape function for the four-noded element. So it is 1 at node 1. So n1 is 1 at node 1, and it is 0 at node 2, 0 at node 3, and 0 at node 4. And if you think about it, you cannot fit a plane through this. So it will be slightly curved, and it's not actually linear, it's bilinear. So this is why we call it bilinear. Okay, now you can increase the order and move into quadratic. So for this case, for the three-noded, we have u to be equal to a xi plus b eta plus c. Now you can push things further and have things like u is equal to a xi squared plus b plus b eta squared plus c xi eta plus d xi plus f eta plus, I don't know, g. So you have 1, 2, 3, 4, 5, 6 components, and then you can increase the order further. So this would be 6-noded element. Okay, so you can work with basically any order of elements is basically how you represent the shape functions. And you can do this for any order of elements you want. I'm going to talk slightly about that here. So and I'm going to specifically talk about, probably is easier to see things in four-noded elements. So I'm just going to do it for four-noded elements. So this is the linear element you have in the nodes. You can refine this one step into quadratic. And then instead of 4 nodes, you have 9 nodes. Or you can refine it even further. So this is linear, so the polynomial order 1. This is polynomial order 2. And you can even have polynomial order 3. So this is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this is polynomial order 3, and you can keep refining this as far as you want. The same also applicable for triangular elements. So this is p equal 1. If you have 6 nodes, just like the function I've written, this is p2. So this is basically just this function here. You have 6 nodes, and you can keep refining this as much as you want. I mean, there's a specific way to refine these or increase the order of these elements, and the specific way can be defined in, I don't know if you have seen Pascal triangle. So the Pascal triangle will define the order by, or the way you can increase the order of these elements. Now, just one note to mention about these four-noded elements. So the four-noded elements can be refined into, if you're looking into P2, into 9-noded elements or 8-noded elements. So this is the nodes, or this is the elements that is implemented in loosars. So it can go in 2 different ways for P2. So you ignore the central node or you keep the central node. Also for P3, you can have only the nodes on the boundaries. or include the nodes on the center. So this family of elements, this family here, is called the serendipity family, and this family here is called the Lagrangian family. So this family of elements is called the Lagrangian finite element. This is called the serendipity finite elements. And this is the main two families of elements, if we're talking about this class of elements. All right, and similar thing could also happen in the triangular elements. So you could have Lagrangian and serendipity elements also for triangular elements. Okay. Now, obviously, this would also be reflected in the stiffness matrix, would be reflected in the shape functions. All the expressions would remain very much the same. It's only just does they get lengthier and lengthier. There's more terms into them. Now, you can have a combination of different type of elements if you want. You can have linear and quadratic elements combined together as long as you match the nodes together. So if there is a node that will match things together, then this is fine, because these elements would always need to be connected at the nodes. But if you don't have a connector for this element here, if you don't have anything to merge these nodes into, then in this case you will have a hanging node, and this is not going to work. This is going to be a problem. Okay, so you can combine any type of elements together. It's just that you really need to be careful not to have any hanging nodes. One note about the quality of the elements. So if we are talking about the one-dimensional elements, so this is different, because in one-dimensional elements, you don't have any quality, so to speak. So you have elements small or big, it doesn't really matter. You just change their length. Whereas in 2 dimensions, the quality of the elements would change. So first of all, you can, or probably one way to check the quality of your elements is to use a circle. So you use a circle to pass through the nodes, and then you use a circle that would touch the edges from the inside. And the area of these two circles, so it is basically R1 divided by R2 squared. So it is the area of this circle, the area of this circle divided by the area of this circle, and the number will need to be as large as possible. Now, if this number is very small, is very, very small, so much, much smaller than 1, then in this case, you will have a very poor quality element. If this number is close to 1, I mean, it's not possible to reach 1, obviously, but if it is possible to get it as close as possible to 1, then you have the best quality element. So the good quality element would be an element which all the sides are equal, and a poor quality element will be a very thin element. So if you see the element is very thin, if we're talking about the quadratic element, so if you have an element like this, this is a poor quality element. Apply just the same concept. So think in terms of the area that is passing through, or the circle that is passing through the corners, and the area that would touch 2 sides and not cross any other side. So you'll see that this is really small compared to the other one. But just visually check them. If your elements are really very thin, then in this case, your element is poor. If your element is large, if your element is bulky, then in this case, your element is of good quality. Now, how this is going to impact the calculations, I'm going to show you these 3 meshes. Now, these 3 meshes are trying to recover this surface here. So think about this as a surface, curved surface, and you are trying to recover this curved surface here using these 3 different meshes. Now, all the 3 meshes will have 200 triangles. So if you count the number of triangles, you'll see that all of them are exactly the same number of triangles. Now, the first mesh is capable of capturing the curved surface much better than the second one, and still much better than the third one. Now, you still have 200 elements in all the meshes, but the performance of this one is much better than the performance of this one. So you need to look into what direction you really need to have more elements into and have better quality elements if possible. All right. So the local coordinates, I've discussed that. So the mapping process between the local coordinates and the global coordinates is what we just discussed. All right. Do you have any questions? Because yes, it's exactly the same behavior. So once you have a distributed load, then the linear element will behave poorly. You need to have many of them. If you have a quadratic element, the quadratic element would work with a distributed load much better. So it is pretty much exactly. So whatever you have learned or everything you have learned about this one-dimensional problem would still be applicable to the two-dimensional problem unless I tell you that this is a different situation. So everything you have learned so far is still completely valid for the two-dimensional problem.